In this video, I'd like us to look at 3D vector addition and vector subtraction. Now, this isn't going to be any more complicated really than our 2D case. So we saw in our 2D case, if we had a vector A equal to x1, y1, and a vector B equal to x2, y2, we saw that A plus B is equal to a vector, and the vector's components, the first component of our result, is equal to the first component of A added to the first component of B, so it's equal to x1 plus x2. The second component of our result is equal to the second component of A added to the second component of B, so it's equal to y1 plus y2. So this was our 2D case of vector addition. Well, we know that our 3D vectors introduce that third component. They introduce the z component. So our 3D vector A would have x1, y1 and z1, and our 3D vector B would have x2, y2 and z2. All that changes in our result is that our result is going to become a three-dimensional vector. And the only difference here is that we then, for the third component of the result, we add the third component of A to the third component of B. So it's a simple extension where we now have this third component as Z1 plus Z2. So there's really no difference. We still go through component by component and we add the likewise components. We add component 1 to component 1 to generate the first component of the result, just as in our 2D case. We add component 2 to component 2 to generate the second component of our result, again just like in our 2D case. And now we add component 3 to component 3 to generate the third component of our result. So this is the new little bit of theory for 3D, but it's a very simple extension of our 2D case. And just like our 2D case, vector addition is commutative, which means that A plus B is equal to B plus A. And just like our 2D case, subtraction is going to work in the exact same way. So if we had A minus B, that means we're going to have x1, y1, z1 minus x2, y2, z2. What we saw in our 2D case, we take the first component of our first vector, which would be x1, and we subtract the first component of our second vector. Well, it's the same here. For our first component of the result, we take the first component of the first vector and subtract the first component of the second vector to generate the first component of our result, so x1 minus x2. We're going to do the same thing now for our second component, so second component of our first vector minus the second component of our second vector to generate the second component of our result, so y1 minus y2. And now, because it's 3D, we've got a third component. We're going to repeat that process for the third component of our result. The third component of the first vector minus the third component of the second vector to generate the third component of our result. So z1 minus z2. So there's nothing really complicated here. It's a simple extension of the 2D case. And just like the 2D case, vector subtraction is not commutative, so A minus B does not equal B minus A. Hopefully that's very obvious because it's a simple extension of the 2D case. We looked into why this was the case in great detail with the 2D case. We have the exact same thing here, we've just introduced a third component, so hopefully it's obvious why this is the case. So we can see that our vector addition and our vector subtraction, there's really nothing more to them when we're dealing with the three-dimensional vector as opposed to the two-dimensional vector. Now we saw in 2D, when we were adding two vectors together, if we had a vector A and some vector B, we saw in 2D, if we had A plus B, this is the same as saying we travel along the length of A, and once we've got to the end of A, we then place vector B, and then we travel along the length of B, and we said that A plus B is the same as having travelled from the start to the end of this chain of vectors, if you will. So it's equivalent to the vector that runs from the start to the end. And we saw this in our 2D case. We saw how this was true. We used numerical examples to show this was true. Well, it's the exact same thing in 3D. We could imagine these as being three-dimensional vectors. If we're adding three-dimensional vectors, as long as we start with our first vector, working left to right, place that, travel along to the end of that vector. Once we've got to the end of that vector, we then start our next vector. We place the start of that vector at the end of our vector and travel along to the end of there, and likewise throughout the addition or subtractions that we're doing. And then from the start of that chain to the end of the chain, that vector is the equivalent of the vector result here. And we can actually prove this if we were to come up with a couple of examples. So if I was to have a vector that was 2, 0, and -1, say, and another vector that was 1, 3, and 4, let's say. Now, if I was to add these together, we know that a plus b is going to be equal to, just like in our 2D case, we take the first component, so 2, and we add that to the first component of the second vector, so +1. We take the second component, 0, add that to the second component of the second vector, so add 3. And we take the first component, or rather third component of the first vector, which is -1, and add that to the third component of our second vector, which is 4, which in this case is actually going to give us the vector 3, 3, and 3. So what we're looking for in terms of the graphical representation is a vector 3, 3, 3. Now it's going to be hard to draw this in 3D. So what I'm going to get you to do instead is what I'm going to do is start down here and imagine we're starting at the origin. So I'm not going to try and draw this in 3D because that's going to be quite challenging, but what we can do is think about our position in space as we travel along these vectors. So the first thing we're doing is traveling along vector A. So we're traveling along some vector A, and we know that vector A is equal to traveling 2 units in x, no units in y, and a -1 unit in z. So if we started at the origin and we've traveled 2 units in x, that means we're going to be at 2 in x. If we've then traveled no units in y, so we started at the origin but traveled no units in y, we're still going to be at 0 in y. And if we started here at the origin but traveled -1 units in z, we're going to be at -1 in z. If we then, from there, travelled along vector b, so we're now at 2 in x, 0 in y, and -1 in z. If we then travelled along vector b, we're going to travel 1 unit in x, 3 units in y, and 4 units in z. So we're going to travel 1 unit in x, so if we started at 2 in x and travel 1 in x, that's going to get us to the point 3 in x. If we started at 0 in y but travelled 3 in y, that's going to get us to 3 in y. And then if we started at -1 in z but we're now travelling 4 in z, that's going to put us at 3 in z. So we can see our final vector here, which is our vector a plus b, just as in the 2D case that travels from the start of our chain to the end of our chain. We can see that this vector starts at the origin, 0, 0, 0, and travels to this point, 3, 3, 3. Therefore, we know this vector must have the components 3 in x, 3 in y, and 3 in z. If we start at the origin, so 0 in x, and we travel to 3 in x, that must mean that we have an x component of 3. Likewise for y, we started at 0 and travelled to 3 in y, therefore our y component must be 3, and the same for z, we started at 0 and travelled for 3, so we must have a component of 3 in z. So hopefully you can see the graphical representation. Even though I'm dealing with just a 2D whiteboard, it's quite hard to draw 3D diagrams. Hopefully you can see that indeed it's the same as in our 2D case. So that means no matter what the combination of vectors we're doing, if we were adding together 3 or 4 different vectors, so if we had a plus b plus c plus D, and these were all 3D vectors, we'd have the same as the 2D case. Each of these vectors would be a directed line segment. If we started them anywhere in Cartesian space, because they're free to travel around Cartesian space, so we pick some point, and then if we were to lay them end to end, so we travel along the length of A, once we've got to the end of A, we then look at B, so we then travel along the length of B. Once we've got to the end of B, we then look at C and travel along the length of C. Perhaps that comes down this way. Once we've got to the end of C, we then look at D and travel along the length of D. Perhaps D comes down like so. The resultant vector that we could call E is going to be from the start of our vector chain to the end of our vector chain, and that's the same in 3D as it was in 2D. Also the same in 3D as it was in 2D is the graphical representation when we're subtracting vectors. So if I was to have A minus B, we saw in the 2D case that we'd travel along the length of A, and then if B went off in this direction, what we'd actually do is we saw first, when we were dealing with addition and subtraction, we said, well, we'd place B, but we place it so its end touches where we'd got to, and we travel in the opposite direction down B. But then when we saw how we were dealing with scalars, we said, well, we can think about this as being minus 1 times B, which gives us minus B. And so if we think about it like that, we can think about traveling down minus B. It's almost as if we're taking A plus negative B, and because of that we get to where we got to at the end of A. We then travel down the vector which is minus B, which we know is the same as B, only the direction has been reversed. We're traveling in the opposite direction, and the result of A minus B is again from the start of our chain to the end of our chain. So we saw that in 2D. It's the exact same thing in 3D. If this was a 3D vector and this was a 3D vector, wherever we were starting in 3D space, and then we travel along our first vector and then the opposite direction of our second vector, wherever we then got to in 3D space, obviously these are going to be 2 points, the vector that travels between those 2 points is equal to A minus B. So it's the same thing in 3D as it was in 2D. And therefore a logical extension, we saw if we had a really complicated equation that had additions and subtractions, for example A minus B plus C minus D, for example, then in 2D we saw this might look something like this. If this was A and this was B, then we'd travel down minus B. Then perhaps this was C, going off in this direction, and perhaps this was D, but we're traveling in minus D, so we travel down this way. In the exact same way, from the start of our chain to the end of the chain, that vector is the equivalent, we could call this E, is the equivalent of our equation here. So we saw that in 2D, it's the exact same thing in 3D. There is no difference. The only difference is our vectors exist in 3D space. They can travel in X, Y, and Z, but in terms of those directed line segments, if you place them end to end and form a chain of vectors, the start to the very end, that vector is the equivalent of our equation. So in terms of the graphical representation, they are going to be exactly the same. So there's really nothing to it, and you're going to find this with everything we've looked at so far with 2D vectors. There's really not that much more involved when we deal with the three-dimensional case. But just to check that you do fully understand how we add and subtract three-dimensional vectors, I'm not going to ask you to do graphical representations, because even I'm having a hard time drawing three-dimensional diagrams here on our whiteboard, so I'm not going to ask you, like we did with the 2D case, to actually draw these out, but I will set some questions where you can practice adding and subtracting some vectors. So I'm going to bring up a new whiteboard, and question 1, I'm going to ask you if we have A equal to, let's say A is equal to 1, minus 2, and 3, B is equal to 3, 7, and 10. I'd like you to work out what A plus B is equal to, please. So go ahead and pause the video, and when we come back I'm going to work through the solution here on the whiteboard. Okay, welcome back everyone. So a nice simple example to start out with, simply adding two three-dimensional vectors. So we know that this is equal to 1, minus 2, and 3, plus 3, 7, and 10. So let's scroll down. So we know when we're adding our three-dimensional vectors, much like when we're adding our two-dimensional vectors, we take the first component of the first vector and we add that to the first component of the second vector, and that's going to give us the first component of the result. So 1 plus 3 is the first component of the result. We take the second component of our first vector and add that to the second component of our second vector, and that's going to give us the second component of our result. So minus 2 plus 7. And then we take the third component of our first vector and add that to the third component of our second vector, and that's going to give us the third component of our result. So 3 plus 10 is the third component of our result. So if we were to work this out, our result is a vector with 1 plus 3 is 4, minus 2 plus 7 is 5, and 3 plus 10 is 13. So we have an x component of 4, a y component of 5, and a z component of 13. So hopefully you had no issues following along with that. If you did get stuck anywhere, firstly make sure you understand 2D vector addition, because this is directly an extension of 2D vector addition, and as long as you're comfortable with that, then the only thing that really might have thrown you is the fact that we've got these third components. And again, there's nothing different here. We just take the first component, add it to the first component to generate the first component of the result, second component to the second component to get the second component of the result, third component, add that to the third component to get the third component of the result. So there's really not that much different here. We've just included an additional coordinate, an additional component. So that's our first question. I'm going to set a couple of additional questions. So let's set question 2, and in this case I'm going to set a subtraction. So let's say we had a vector A equal to, let's say 5, 6, and 9, and a vector B equal to 3, 2, and 1. So what I'd like you to calculate, please, is A minus B. So go ahead and pause the video, and when you come back I'm going to work through the solution here on the whiteboard. Okay, welcome back everyone. So a nice simple vector subtraction. So we know this is equal to 5, 6, 9 minus 3, 2, 1. And we know if we're doing a vector subtraction, it's going to be a vector as a result. It's going to have 3 components because our vectors have 3 components. And we take the first component of the first vector and subtract that from that, this first component of the second vector to generate the first component of our result. So that's 5 minus 3. It's going to give us the first component of our result. We then take the second component of the first vector and subtract from that the second component of the second vector to get the second component of our result. So 6 minus 2. We then take the third component of our first vector, subtract from that the third component of our second vector, and that will give us the third component of our result as 9 minus 1. We can then work this out. So 5 minus 3 is 2, 6 minus 2 is 4, and 9 minus 1 is 8. So our resultant vector of A minus B is equal to 2 in X, 4 in Y, and 8 in Z. Fantastic. So I'm going to set one last question. So question 3. And this question is going to give you 4 different vectors. So vector A, which I'm going to say is 7, minus 2, and let's say minus 3. A vector B, which is, I'm going to go with 2, 0, and 1. A vector C, which is, let's say 3, 4, and 5. And a vector D, which is equal to, I'm going to go with 10, 8, and 3, say. And what I'd like you to evaluate, please, is A minus B minus C plus D. So what is that equal to? And I will point out, just like in the 2D case, we're going to be working from left to right here. So I will point out that it's no different to the 2D case. If we have a more complicated equation like this, you simply work from left to right. So with that, please evaluate A minus B minus C plus plus d, and then when you come back, I'm going to work through the answer here on the whiteboard. Okay, welcome back everyone. So this is going to give us vector A is 7 minus 2 minus 3, so 7 minus 2 minus 3. We're going to subtract from that our vector B, which B is 2, 0, 1. So 2, 0, 1. We're going to subtract from that our vector C, which C is 3, 4, 5. And then we're going to add to that our vector D, which D is 10, 8, 3. So that means our resultant vector is going to be equal to 7 minus 2 minus 3 plus 10 for the first component. So 7, working from left to right, 7 minus 2 minus 3 plus 10. So 7 minus 2 minus 3 plus 10 is the first component of our resultant vector. For the second component of our resultant vector, we're interested in the second components of our vectors. So we have minus 2, minus 0, minus 4 plus 8. So minus 2, minus 0, minus 4 plus 8. And then for the third component of our resultant vector, we're interested in the third components of our vectors. That gives us minus 3, minus 1, minus 5, plus 3. So minus 3, minus 1, minus 5, plus 3. So this is equal to 7 minus 2 is 5. Minus 3 is going to then give us 2. And if we add 10 to 2, that's going to give us 12. Minus 2 minus 0 is still minus 2. Then minus 4 from that is going to give us minus 6. If we add 8 to that, that's going to give us a positive 2. Minus 3 minus 1 is going to give us minus 4. Minus 5 is going to give us minus 9. And then if we add 3 to minus 9, it's going to give us minus 6. So the resultant vector is 12 in x, 2 in y, and minus 6 in z. So hopefully you can all see that there's really not that much to vector addition and subtraction in 3D. It is the exact same thing as we saw in 2D with just an additional component. So again, to recap, we've already seen that it's just the same thing but with this additional component that we need to deal with in the exact same way as we dealt with the first and second components in 2D. And we also discussed that in terms of our graphical representation, again, it's equal to a vector that goes from the start to the end of a vector chain, only in this time our vector chain is going to, of course, exist in 3D, not 2D. But when we're dealing with addition and subtraction, the way that we dealt with those vectors and connecting those vectors together in 2D is the exact same thing, but now we're connecting line segments together in 3D, and the vector that goes from the start to the end of that chain is the vector of our result. So with that, that is going to conclude this video, and in the next video we're going to continue our look at how we can take our 3D vectors and apply the operations we've already looked at in 2D onto those 3D vectors.